Imagine if there was a single map that could chart the behaviour of nearly any system in the universe. From galaxies swirling in space to neurons firing in your brain. A map that shows why markets crash, hurricanes form, and life itself tends to evolve on the razor's edge between order and chaos. This is the complexity map, the framework that unites physics, biology, and intelligence under a single mathematical language. By the end of this video, you'll see how everything from evolution to AI follows the same hidden rules of complexity, and what that means for how we understand change itself. But to understand this map, we need to understand what we're measuring. Every dynamical system can be described by two fundamental quantities. The horizontal axis separates two worlds, the predictable and the completely random. On the far left you have the pendulum. It swings back and forth. If you know the laws of physics and its current position, you know its entire future. It's completely predictable. On the far right you have the coin flip. Heads, tails, heads. Can you predict the next one? Absolutely not. It's purely random. This spectrum from perfect prediction to pure randomness is what we call entropy. Technically, entropy tells you how much information you'd need to fully describe what happens next. With a pendulum, you don't need any more information to predict what happens next. Zero entropy. With a coin flip, you can't predict what's going to happen next. Maximum entropy. Scientifically, this is called Shannon entropy, and it's measured on a scale from 0 to 1. And most real systems, they live somewhere in between. That's why we need something else we call complexity. So if entropy is about predictability, what is complexity? It took me a while to fully understand complexity, but I like to think about it like this. The key is to look at what emerges. When a system follows its rules, what kind of patterns does it create? Listen to the pure random static of white noise. It's all surprise, but no patterns emerge. It has zero complexity. Now, picture a hurricane or a tornado. It's a collection of countless air and water molecules, each following the same simple laws of physics. But what emerges is something more, a vast self-organising spiral with its own structure and logic, an eye, a path, a life cycle. This isn't written into the rules for any single molecule. That emergent structure is complexity. It's a measure of the hidden organisation and structured information a system creates, beyond the randomness of its parts. Now, let's add a very important feature to our map, a boundary known as the maximum complexity curve. Notice it has an iconic arch shape. It starts low, peaks in the middle, and then falls again. This isn't an accident. It reveals a deep truth about the universe, which we can see unfold in a simple cup of coffee. Imagine a cup of coffee with cream on top. At first, they're separate, perfect order, but also simple to describe. Low entropy, low complexity. Now, give it a stir. You'll see an explosion of intricate, swirling patterns forming. This is the sweet spot, full of rich, evolving structures. It's unpredictable, and it has high complexity. Keep stirring, and it all becomes a uniform, random brown. Maximum entropy, but again, trivially simple to describe, so low complexity. That journey from simple order through rich structure to simple randomness is the maximum complexity curve. It proves that complexity requires both structure and unpredictability. Profoundly, it means that nature has a theoretical upper bound on how complex any system can be at a given level of randomness. Now, here's something remarkable. We don't find systems evenly scattered across the map. Real systems cluster in specific regions. The colours of these clusters tells us, on a relative basis, how densely populated these systems are, from dark blue, being very scarce, to bright red, highly dense regions. The brightest red clusters form along the maximum complexity curve itself, especially in the central region around intermediate entropy and high complexity. This is the densest zone on the entire map. Near the peak of this curve, the sweet spot of maximum complexity is where the magic truly happens. It's where brains emerge with consciousness, where artificial intelligence learns to think, biological systems emerge, and where life organises into intricate living systems. Here's where you also find chaotic systems, weather patterns, and many aspects of financial markets, all the complex adaptive systems that make the world interesting. This is the edge of chaos. This is where nature prefers to operate. And there are good reasons for this distribution and clustering, which we'll explore in just a moment. Let's begin with very simple systems. Pendulums, metronomes, planets revolving around the sun, perfect sine waves. Periodic order, completely predictable, and zero surprises. Also, near zero complexity, there's nothing complex about a repeating pattern. There are no hidden rules to learn, no deep structure to uncover. But notice something crucial. This region is sparse. Real systems almost never live here. But why is that? Because perfect order is fragile. Real pendulums have friction. Real clocks drift. Nature avoids this extreme because any noise destroys it. As entropy increases and noise creeps in, we enter the zone of intermittency. Intermittency is a zone where systems alternate between long periods of calm, orderly behaviour and sudden bursts of chaotic activity. We see this in financial markets. Long periods of calm can suddenly be punctuated by sudden flash crashes, chaotic bursts of trading, then back to normal as though nothing happened. Or phantom traffic jams. Traffic flows smoothly, then suddenly everyone's braking for no visible reason, then smooth again minutes later. The system sits balanced on a knife's edge, neither fully stable nor fully chaotic. Small perturbations can tip it one way or the other, creating on-off switching. Intermittency appears across nature, suggesting it's a fundamental principle governing how systems transition between states. But this region has two faces. Some systems pass through intermittency briefly, as a transient warning before collapse or reorganization, but others inhabit intermittency persistently, flickering between states as their normal mode of operation. Intermittency is nature's warning system. Foreshocks precede earthquakes. Arrhythmias precede heart attacks. These breaks in rhythm are signals that a system is on the edge of something. But some systems don't leave intermittency. They live there. For example, your brain hovers near the edge, exhibiting controlled fluctuations between order and chaos. This isn't malfunction, it's optimization. Neural systems maintain themselves at criticality, where information processing and adaptability are maximized. Evolution does this. Learning systems do this. So the question becomes, what's the difference between intermittency that precedes collapse and intermittency that precedes innovation? The answer lies in the densest, most vibrant region on the entire map. Maximum complexity. Where chaos meets adaptation, where unpredictability becomes the source of power. So let's explore the bright red heart of the map and understand why chaos isn't randomness and what brains do that chaos can't. Most people assume that chaos means randomness. But that's exactly wrong. Deterministic chaos is absolutely not random. As the name suggests, it's governed by a few simple rules. A classic example to illustrate deterministic chaos is the double pendulum. The trajectory spirals out, loops back, spirals out again, loops back, creating intricate structure that never repeats exactly. It's deterministic but unpredictable. Order that looks random. Technically, this is called sensitive dependence on initial conditions, popularized as the butterfly effect. Tiny differences amplified exponentially. In any chaotic system, such as the weather or financial markets, impossibly small differences doom precise long-term prediction. But unpredictability is not randomness. The system has structure. The trajectory follows what's called a strange attractor, a hidden geometric pattern in phase space that the system's behaviour traces out. Its trajectory never perfectly repeats itself, but is always confined to this specific shape. That shape is known as a fractal. Fractal patterns also appear elsewhere on the map, but in this zone, the fractal is the deterministic but infinitely complex hidden geometry of the dynamics. The system is hard to predict. It has fairly high entropy, but it has deep hidden structure and therefore high complexity. But critically, a deterministic, chaotic system does not adapt. It doesn't learn. It doesn't reorganize itself. It follows its strange attractor indefinitely. The attractor shape is fixed. The system cannot modify its own rules in response to experience. It's deterministic, but non-adaptive. But true complexity, maximum complexity, requires something fundamentally different. Look at a brain. A biological brain has chaotic neural dynamics. Individual neurons fire seemingly randomly, with sensitivity to tiny perturbations. But the brain doesn't just exhibit chaos, it learns, it adapts, it reorganises its structure in response to experience. This is genuine complexity. A complex adaptive system combines chaos and organisation in creative tension. It has many interacting parts, billions of neurons, trillions of connections, or millions of cells, or thousands of organisms with feedback loops between different organisational levels. Some interactions generate chaotic fluctuations, but other interactions modulate those fluctuations, organising them into adaptive structures. The system maintains core identity while responding flexibly to the environment. It has memory. History matters. This is why complexity reaches its true peak here. Not chaos alone, that's rigid and unadaptive. Not organisation alone, that's brittle and cannot respond to novelty. But the coexistence of both, chaotic fluctuations held in creative tension by self-organising feedback, structure and flexibility, rigidity and adaptability, determinism and responsiveness. Why does nature concentrate here at maximum complexity? Because this is where adaptability maximizes. The system is robust yet flexible. It can fail gracefully, lose one component and others compensate. It can learn, incorporate new information and modify behaviour. This is why evolution drives systems towards this region. Natural selection has discovered over billions of years that maximum complexity is where systems thrive and can respond to unforeseen challenges. A rigid system dies when the environment changes. A chaotic system has no capacity for learning. But a complex adaptive system at maximum complexity learns, evolves, and adapts. But here's a puzzle that stumped scientists for decades. How can you get order from pure randomness? No learning required, no intelligence, no rules being applied. Just countless random events piling up, and yet structure emerges. Look at these three images: a coastline, an earthquake distribution, and stock market crashes. Completely different fields, completely different causes, yet they share an identical mathematical pattern. The same formula describes all three. How is that possible? The answer lies in a mechanism so elegant, so powerful, that it may be more fundamental to nature than anything we've discussed so far. This is the concept of self-organised criticality. To help understand this, imagine dropping grains of sand one by one onto a pile. Most grains cause nothing to happen. Some cause a few other grains to shift, but every so often a single grain will trigger an avalanche. A cascade of movement that can be small, medium-sized, or occasionally enormous. But no one is planning these avalanches. Each grain falls randomly, yet the system as a whole organises itself into a critical state, balanced right at the edge of collapse. The signature of this critical state is a specific mathematical pattern called a power law. This is the second region where we see the signature of fractals, though here fractals are the statistical signature of collective behaviour. The system generates events at all possible scales, from tiny to catastrophic, with a frequency that follows a specific mathematical fractal pattern. The data itself, when plotted, reveals a self-similar structure. Self-similarity means a structure or pattern that looks the same at every scale. This phenomenon is surprisingly common. For example, the measured length of a coastline depends on the size of your ruler, a hallmark of a fractal shape. In financial markets, the fluctuations of stock prices often exhibit these characteristics, with periods of calm punctuated by booms and busts, which look the same no matter how much you zoom in or out. But just like deterministic chaos, these systems don't learn. A sandpile doesn't adapt. An earthquake network doesn't have memory in the sense of conscious adaptation. Individual events are fundamentally random. You cannot predict the next grain's impact or the next earthquake's exact location. But here, there's no hidden deterministic rule like in chaos, generating the randomness through iteration. And there's no adaptive learning like in complex systems, generating structure through conscious reorganization. The structure exists only in the statistical correlations across time and space. Those systems in this region don't reach maximum complexity. they can create beautiful, structured, fractal patterns that define so much of our world. We began our journey at one extreme, perfect order, sparse, fragile and rare. We've travelled through intermittency, through chaos, through criticality, regions bursting with structure and life. Now we arrive at the opposite extreme, perfect disorder. And here's what's remarkable. It's just as sparse, just as fragile, and just as simple as where we started. White noise is maximum entropy, pure randomness, no correlations, no patterns, no structure. Each outcome is independent of the previous one. This is where we find coin flips, the cosmic microwave background, thermal noise in electronics, completely degraded signal. Pure randomness is one of the simplest things to describe. Perfect order is fragile, perfect randomness is rare. Only the middle, where structure and unpredictability coexist, is where real systems thrive. So as we zoom out, we see two distinct paths leading to maximal complexity. On the left we have the path of one becoming many. This is the path that starts with a single perfect and often simple rule, like Newton's laws governing a double pendulum. There is no randomness, just a clockwork mechanism. As we increase the entropy, the power of feedback and iteration kick in. Tiny differences get magnified at every step, and its long-term behaviour becomes completely unpredictable. That one simple rule slowly reveals its hidden structure and unfolds into a universe of infinite, unpredictable beauty. On the right, we have the path of many becoming one. This is the universe of emergence and self-organisation. It starts with the exact opposite, countless independent random parts. There is no master plan, no central controller. As entropy decreases, the action of each agent influences its neighbours, kicking off powerful feedback loops. As these loops synchronise, feedback creates emergent structure. In the most sophisticated systems, brains, ecosystems, evolving populations, the system becomes reflexive. It monitors its own state and modifies its behaviour. This is the engine of true learning. The system builds memory, anticipates the future and adapts. This is emergence. This is self-organisation. Multiple independent random components generate structure and complexity through their collective interactions, and many becomes one. Now let's zoom back out and see the entire map. We've travelled across this map, visiting each region, seeing what systems live where. But now let's ask, what does this all mean? Why should you care? This framework gives you a helpful lens to think about every system in the universe. Financial markets, neural networks, artificial intelligence, economies, societies. When you think about nature through this lens, it gives you a new perspective about the forces driving a system, how it relates to others in a similar space, and how it might evolve. This framework is universal. The same principles that govern weather also govern your heartbeat. The same mathematics that explains stock market crashes explains earthquake sequences. The same boundaries that limit computer complexity limit biological complexity. It all fits. Evolution has discovered this edge over billions of years through natural selection. Systems that can operate at maximum complexity, that can be both structured and adaptive, both stable and flexible. Those systems survive. Those systems thrive. Those systems spawn even more complex systems. This map gives us a view into nature's blueprint. It's the design pattern of how complexity arises in the universe. Understanding it changes how you see everything, including your own decision making. There's an interesting exercise you can do with this map. Find a system you encounter today, anything, your coffee brewing, your commute, your inbox, a news headline, and ask, where is it on the map? Does it make sense? Does the framework predict what happens next? Some people find it trivial. Others say it changes how they see everything. Try it, and if something surprising comes up, something the framework predicts that actually happens, throw it in the comments. Let's see what you find. I'm genuinely curious what systems people recognise in their own lives. Drop your answers below. And thanks for watching.